Okay, so the importance in doing distributed load problems is not to be able to do the integration, because you already know the integration from math and physics. But rather, what's important about distributed load problems is in engineering, we're looking at a body that has a number of distributed loads on it. For instance, bring it over here, Kyle. For instance, if I have a skyscraper, and there's a skyscraper next to it like this, and then there's a skyscraper next to it like this, when I have wind coming in, this building, let me draw it the way you're used to it being drawn now, distributed loads. I have a distributed load of wind coming in, like this. And if the wind goes the other way, I have a distributed load of wind going like this. I need to figure out how this body is going to respond with multiple distributed loads. What about another example is if I have a pile, a foundation, that's holding up something up here in the water, or no, let's do a retaining wall. A retaining wall. On one side, it has soil, and on the other side, this is the symbol for water. There's water here. Well, this retaining wall right here is being subjected to a triangular distributed load due to the water. And on this side, based on the water. And then it also has a distributed load on this side based on the soil pressure. So this is soil pressure and this is the water pressure. And again, so we have to look at this body, this retaining wall, and analyze it based on multiple distributed loads it's going to have. So that's what our main focus is in statics, is looking at a body and analyzing it with many distributed loads on it. So let's look at the first example we have. We're looking at a 9-foot beam, and it's subjected to gradually decreasing distributed loads. So what I'm going to need to do is divide this up into sections so I can analyze each section. So how would you want to divide it? We could divide it and say the first section, section 1 has 200 pounds per foot, section 2 has 150 pounds per foot, and the third section is 100 pounds per foot. Or can I look at this whole beam of 9 feet and say the whole beam is subjected to 100 pounds per foot? And then this part of the beam, the 6-foot part of the beam, is subjected to an additional 50 pounds per foot. And then the last one has another 50 pounds per foot. So I can divide it up any way I want. But I'm going to look at it as 200, 150, and 100. So this is section 1, this is section 2, and this is section 3. So let's look at section 1. Do we need to do integration? No. We know the force is going to be equal to 200 times 3, 600 pounds. And where is it going to be located? Well, it's going to be located right here, right? Which is 1.5 over. So let's call this x bar. And x bar, so this is force 1, and x bar 1 is going to be 1.5 feet over. Okay? Let's look at section 2. Section 2, F2, is going to be 150 times 3, which is 450 pounds. And x bar 2, remember I'm still measuring x bar from the end. So we know that x bar is going to be 1.5 here, but we already have 3, so it's 3 plus 1.5, which is 4.5 feet. And then section 3, our force is 100 times 3, 300 pounds. And our x bar 3, we know is going to be 1.5 here, but we've already gone 6, so it's 6 plus 1.5, so it's 7.5 feet. So right now we've reduced this to an equivalent system of beam with 1.5 over, 4.5 over, and 7.5 over. We have a force of 600 pounds. We have a force of 450 pounds. And we have a force, sorry, I didn't draw this to scale. And a force of 300 pounds. Does everybody agree that this beam is being subjected to 3 distributed loads, which is equal to the same beam being subjected to 3 point loads? But can I simplify it even more? Can I simplify it more to a 9-foot beam with one point load? This is an equivalent system problem. Because now I have a problem which is very similar to the ones we looked at before, where I have one body, 3 forces being subjected. How can I determine what the equivalent system is? The most simplified form. What would I do? What did we do in all those equivalent system problems? What was the first thing we did? We found the resultant force, the sum of the forces. So 600 plus 450 plus 300. What does that turn out to be? 1,350 pounds. And then what did we do? We did sum of the moments. The sum of the moments about the left end, let's call that 0.0. 600 times 1.5 negative, 450 times 4.5 negative, and 300 times 7.5 negative. And the moment turns out to be -5175, negative 5175 foot-pound is the moment. Now, there were 2 types of equivalent system problems, right? One was a force-moment problem, where we put the force and the moment at the same point. Well, what kind of equivalent system problem is this? It's not a force-moment problem. It's a force-location problem. They want one force at a certain location. So what was the next step in the force location problem? It was to find the distance, the perpendicular distance, which is the absolute value of the moment divided by the force, and it's 5175 divided by 1,350. And that value comes out to be 3.83 feet. So now we have to think about it. Remember, we got absolute value, so this value is going to come out to be positive. But we have to find out where this force is actually. And shouldn't I have, all along, I've never put in the signs. And I should have put in signs all the way from the beginning of this topic. Because our force is negative. All these forces are negative. The forces are negative. The forces are negative, right? They're all going down. So if the resultant force is 1,350, and it's going down, is it going down to the right of 0.0 or is it going down to the left? Well, we got a negative moment. So if our force goes down here and palm goes towards O, it is giving me a negative. So that means this 1,350 pounds does go to the right of 0.0. Let's draw it down to the beam. And what is this distance going to be? This distance is going to be what we found, 3.83 feet. Which means that this distributed load, this system of distributed loads here, we had 1, 2, 3 rectangular distributed loads on the beam. In the end, we found that these 3 forces, these 3 distributed loads on this beam, are exactly the same as having one force of 1,350 going down, set at 3.83 feet from the left side. This and this are exactly the same. Why do we want to do this? Why do we care to have the smaller one? It's because it's a more simplified expression for this. these three distributed loads create the same translational force of 1350 down as this. And these three distributed loads create the same rotational motion at point O of 5175 as this. And it's very important in engineering to take complicated problems and reduce them. So what did we look at today? You've already done equivalent system problems, right? You've already done them. You've done both 2D and 3D equivalent system problems. That's all we're doing when we introduce distributed loads, is we're just doing more equivalent system force location problems. But before you could do that, you have to understand what the distributed load means. So if we have a distributed load of 200 pounds per foot, we need to understand how this is the same as a point load. And that's what we did as the intermediate step.